All right. Good morning, everybody. Let's see. So, don't really have many announcements this morning. I think you have a homework due Friday, so we'll have office hours Wednesday and Thursday as usual. If you have questions on that, let me know. Let's see. One thing I wanted to point out again about this homework, I briefly mentioned it last time, but there's two parts to the homework. The second part, again, is this a little bit more involved, or I don't know, it's not that difficult. It's a different thing from what you've seen before, probably, and I'll give you a little bit more guidance on this. So the idea is that you have in this homework problem, you have two fin surfaces. Normally, for a fin surface or extended surface, you're going to have the model itself of the temperature in, say, X for the extended surface. And then you have some temperature, some condition, some boundary, or something happening outside of the domain that the extended surface is interacting with. So that's usually like convection or something like that. In this one, you're going to solve for the first part. That's normal. The second part is a coupled solution, which means you're going to have two ODEs. All right? So you can use Maple to help you solve for, you have one ODE for the metal part, and you have one ODE for the ice part. And those, you're going to have to find two solutions that both agree on the values of 4 unknown constants. Okay? So it's a little bit different from what you've done before, but it's really just extending the same ideas. So use Maple to help you along the way, and there's some guidance in the homework on that. So yeah, if you have questions on that, we can talk about our office hours are a good option too. Any questions or anything before we get started? Okay. So what we're doing today is we're going to wrap up our discussion of fins, extended surfaces, go through this idea of fin resistance for fin arrays, and then we're going to actually start getting into 2D models or separation of variables. Hopefully we'll get partway into that. We are about, I'd say, half a lecture behind at this point, but it's not really, I don't think, stopping you from doing homework or anything like that, so we'll just keep going at our scheduled pace. Okay, so what did we do last time? Let's look back at what we had. Last time we were talking about the fact that you can come up with solutions for fin resistance from ease. If you go through this this derivation where you say, I know the temperature at the base, TB, and I know something about the condition at the tip of the fin, maybe it's adiabatic. I can come up with solutions that I can tabulate and put in ease and look them up. And these are just different options for geometries. This is now for one extended surface. Right? This is an equation for one extended surface. And you get something like, it's hard to zoom in, you get something like a fin efficiency, eta fin, for a given area in ML term. What happens when you have more than one fin? Right? How do you deal with that? Let's look at this a little bit. All right. So here, remember, is our fin efficiency equation. And the fin efficiency equation is how much heat am I actually sending to the fin, Q dot fin, divided by the maximum possible heat that could go to the fin if the entire fin was at uniform temperature equal to the base temperature. So if we have this fin efficiency, we can also write out something called a fin resistance. So let's actually just let's rearrange this equation to get to the idea of fin resistance. So rearranging, let's solve this equation for Q dot fin. And we end up with Q dot fin is equal to eta fin times h bar AS times TB minus T infinity. All right. Remember, all we need for our resistance is some driving potential and then some stuff multiplying it. And that stuff multiplying it is 1 over the resistance. So this here becomes 1 over R fin. Or just to write that out explicitly, we would say R fin is equal to 1 over eta fin times h bar times AS. So what does the fin efficiency, now fin efficiency is going to be a number between 0 and 1. So what does fin efficiency do to the fin resistance? Right? If you have a fin that is not perfectly efficient, it's going to increase the fin resistance, right? And that kind of makes sense, right? You're thinking about trying to send heat out. Not the entire area is being used, so the resistance to sending heat out goes up. This is the same overall equation as before. It's just you have now this fin efficiency. The other thing to think about is what is this fin resistance actually telling you? It's saying that if I have, let me just draw out some surface here. So let's say I have some surface, and that entire surface is at TB. If I have some portion of this that is attached to a fin, I'll just draw a red box coming off, right? Some portion of this that's attached to a fin. You can model heat loss from this surface as the sum of, say, heat loss from this part, heat loss from this part, heat loss from this part. If you know the fin resistance, you don't need to know anything else about the length of the fin or the temperature distribution in the fin or whatever. You can just model the heat loss directly using that fin resistance. Right? And that's a really maybe obvious thing to say, but it's something that people mess up all the time. So if I say model like a fin array, model the heat loss from a fin array, there's always people that think, okay, I should be going into the fin and modeling the resistance in the transverse direction and all that. No, once you compute your fin resistance, that's all you need, right? That tells you the performance of that boundary between the base and the fin. Okay? So just keep that in mind for what we're talking about next. Okay, so we have our fin resistance. Now let's talk about this fin array. So I want to consider the total heat loss from some device that you'd actually see in practice. Like nobody ever builds a system with one fin. You build a fin array. So let's come up with expressions that we can use to characterize this bunch of extended surfaces mounted to a base. So what we need to do is account for the fact that we have fins, and we can model them, and we have unfinned area. So let's write out an expression for the unfinned resistance, R unfinned. Our unfinned is going to be 1 over h bar times AS of the base, the surface area of the base, minus the number of fins times the cross-sectional area of the fins. Right. So what we're doing is we're saying, I'm going to say that there's convection occurring with the base just like there is with the fins, but it's only occurring on the area that's exposed, so it's just you're taking the balance of the area. All right, so you have these two fin resistance formulas. Now if I'm going to build a model of this, I can use a resistance network to look at the overall heat transfer. So this resistance network might look something like the following. Over here we have TB, and then we have, in parallel, we're going to have heat transfer through fin 1, through fin 2, 3, so on, and parallel heat transfer with the base to the surroundings. So we would go up here and have fin 1. All right, so we call this R fin 1. We have R fin 2, and so on, out to R fin n. And then also in parallel, we're going to have that base, right? So R unfinned down here. And all of those share in common the, I forget what temperature we call it. So T, probably T infinity. Yeah, so they're sharing in common sinking to T infinity. So you could go through and do a resistance network for this. Another way of writing the same thing is to say that I have n resistances there corresponding to the fins and then the one unfinned. So if we actually wrote this out, it might look something instead like this, where we have our unfinned is equal to our, 1 over h bar AS B minus N fin times AC fin. And then down here we would have our R fin times N, which is equal to just...
Wouldn't it be 1 over N?
Yeah, so it's R fin. The N goes in the denominator. It's just NR fins, or I say it backwards, but there are N of these, right? So I'll draw it like this. There are N of these. But you're exactly right. It looks like this. So it's 1 over N fin times eta fin times H bar times AS fin. All right, and those are sinking to, let's see, draw it over here. Those are sinking to T infinity, right? So this is your resistance network model, accounting for all the fins and the base area, and that'll just tell you the heat transfer. You can compute heat transfer. This is TB. Heat transfer going out of the array this way. All right, so that's a relatively straightforward concept, but just some subtleties on the resistances.